Hi everybody. Today we're going to be talking about finding derivatives of functions containing inverse trig functions. So the first thing that I will need you guys to do is pause the video so that you can copy down these formulas. These derivatives are purely formula based. And these are definitely formulas that you're going to want to know and remember for the AP exam. And just a reminder that there's two different ways that we can denote an inverse trig function. You can either see it with that little -1 exponent, or remember that the inverse sign can also be denoted as arc sine. Inverse cosine can be denoted as arc cosine, inverse tangent, arc tangent, and etc. So arc cosecant, arc secant, arc cotangent. So if you see either this notation or this notation, it's asking you to take a derivative of it, we're going to want to use these formulas. So pause the video for a minute, copy those down, and then we'll get into some examples. All right, so the first example, we are looking for the derivative. So we want to find f prime if this function is the inverse sine of x squared minus 1. So you'll notice that our functions or our formulas up here are only given in terms of the derivative of inverse sine of x. So when there's something else other than just x here next to our inverse trig function, this is going to be an indication that we're going to have to use the chain rule. So we need to use the chain rule when it's basically anything other than just x. And we'll see what that looks like when we look at this example. So if we're looking for the derivative of an inverse sine, we're going to want to use this formula up here, the 1 over 1 minus x squared. But again, if this is anything other than x, what we're going to have to do is we're going to have to replace the x here with this quantity. So my first step in my derivative here is going to be my f prime. It's going to be 1 over the square root of 1 minus, and again, the formula says right here we're going to have an x squared, but because we have something other than just x here, it's actually going to be the quantity of x squared minus 1 squared. But again, because this is not just an x here, we're going to need to go ahead and actually use our chain rule, meaning whatever we plugged in for that value of x, or whatever this stuff is on the inside of the parentheses, we're going to need to chain rule this, meaning I need to take this and multiply by the derivative of x squared minus 1. And the derivative, that would just be 2x. And I'm going to clean this up a little bit because I don't want to leave it in this format. There's a couple of steps that I can do here. I could potentially just kind of bring that 2x into the numerator and write this as 2x over the square root of 1 minus the quantity of x squared minus 1 squared. If this is a free response question, you can definitely just leave it like this. But say this is a multiple choice question and this is not an option. Sometimes they will go through the tedious process of actually multiplying this out and then simplifying underneath the square root. So say they wanted us to do that. This would be the 1 minus the quantity of x to the 4th minus 2x squared plus 1 when you FOIL out the x squared minus 1 times x squared minus 1. And then you would want to distribute your 1 or your minus in between there. So this would be 2x over the square root of 1 minus x to the 4th plus 2x squared minus 1. And my 1's are going to end up canceling out because one's positive, one's negative. So another kind of iteration of this derivative would be 2x in the numerator, and then underneath the square root in the denominator, just negative x to the 4th plus 2x squared. So that would be our final simplified derivative. All right, so let's look at another example. This one's still working with inverse sine, but now the inverse sine is actually in the denominator of fraction. So there's two ways that you can go about doing this. If we're looking for the derivative, so dy dx is just looking for the derivative, I can use the quotient rule on this, which will totally get me the correct derivative. So if I use my quotient rule, I can say that my numerator is 1, derivative that's 0. denominator would be my inverse sine of just x here. So this is just x, so we can just use the rule or the formula that we have above that says that derivative of that would be 1 over the square root of 1 minus x squared. So if I go about this using the quotient rule, f prime times g is just going to give me a 0, minus f times g prime is going to give me 1 times this 1 over square root of 1 minus x squared. But then that's still going to be over the denominator squared, so inverse sine squared. And I would want to clean this up, so I don't want to leave it as like a fraction over something squared. So if I do kind of my keep change flip here thing, numerator is -1 over the square root of 1 minus x squared. I'm dividing that by this over 1 technically, so when I do that keep change flip, I'm multiplying by 1 over the inverse sine of x squared. And when I combine those into one fractions, it's going to give me a -1 in the numerator. And then I'm going to have these two quantities being multiplied together in the denominator. So square root of 1 minus x squared times the quantity of inverse sine squared. So that's one way to go about doing this. If you didn't want to use the quotient rule, you could instead rewrite as a quantity to a negative exponent. So I could rewrite this as just y equals the inverse sine of x raised to the -1 power. And that kind of gets rid of the fraction part, so I don't actually have to do the quotient rule. So if I do the derivative this way, I'm just going to need to apply a chain rule here because I have an outside function, I have an inside function. So if I do it this way, my outside function would be to bring the -1 down, keep the inside stuff the same, decrease the exponent by 1, but here's the chain rule part. Now I need to multiply by the derivative of this stuff, which would be the 1 over square root of 1 minus x squared. So if I manipulate this a little bit so that I don't have a negative exponent here, I can rewrite this as -1 in the numerator and then bring that quantity of inverse sine of x squared down to the denominator to make the exponent positive. Still multiplying by this 1 over 1 minus x squared underneath the root, and looks exactly the same as what we have here, just kind of in reverse order. So when I combine those into one fraction, I still have -1 in the numerator. I still have a quantity of inverse sine squared, and I still have that square root of 1 minus x squared. So regardless of which way you do it, you should end up getting the same thing. All right, another example, a little bit different this time because now we're dealing with 1 inverse tangent and 2, we've got a product rule going on here because this is really x times the inverse tangent of the square root of x. So if I apply my chain rule here, or my product rule, I should say, my f would be x, f prime would just be 1. G would be my inverse tangent of the square root of x. And my g prime is going to be where I apply that rule. So if I go back and look at my rule or my formulas here, looks like the inverse tangent derivative is 1 over 1 plus x squared. But again, that's only when this thing is x. In this case, my thing next to it is the square root of x. So what I'm going to have to do is plug the square root of x into this x over here, and then I'm going to have to apply my chain rule. So my derivative would be 1 over 1 plus the square root of x squared, because again, I'm replacing the x in the formula with what I have in here. But here's the chain rule part. Now I need to get the derivative of the square root of x. So remember that the square root of x, we can rewrite it as x to the 1/2 power. So when I do my derivative, bring down the power, so 1/2 x, decrease the exponent by 1. So -1/2. And what I can do is I can clean that up a little bit. So I'm just going to make this simpler because the square root of x squared is just going to give me x. So this is just 1 over 1 plus x. And then I can bring down that x to the 1/2 into the denominator here just to make it a positive exponent. So we'll leave it like this for a second and we'll clean it up once we apply the product rule. So if I apply my product rule, f prime times g is just 1 times the inverse tangent of the square root of x. But then my f times g prime, I'm going to have x times 1 over 1 plus x times 1 over 2x to the 1/2 power. And this is a lot of stuff going on here, and we're going to want to clean it up. So I'm going to bring down that inverse tangent of square root of x. I'm going to bring the x just in the numerator here. X times 1 is just going to give me an x. And then I have a quantity of 1 plus x from my first denominator, and then I have a 2x to the 1/2 in my second denominator. So here, my exponent on this x is really a 1. I can actually simplify these two x terms. And if I think about what that's telling me with exponent rules, I have an x to the first over an x to the 1/2. My exponent rules say that when I have a quotient, I can subtract my exponents as long as the base is the same. So this is really going to simplify to be an x to the 1/2, technically over 1, which really means that these are going to be simplifying to an x to the 1/2 just in the numerator. So bring over the inverse tangent of x. I'm simplifying this to be an x to the 1/2 just in the numerator. And then I still have a 2 in the denominator, and I still have a quantity of 1 plus x in that denominator. So if I wanted to just kind of make this look even prettier, I could, meaning I can turn this back into a root. So I can turn that into the square root of x. If I wanted to distribute out the 2 here, I could. So you could write that as 2 plus 2x. And that would be our derivative. And we could combine these into one fraction if we wanted to, but we would have to make a common denominator, which would make things a little bit more messy. But this is completely fine for a response. All right, and our last example has to do with arc secant. So again, this is just a different way of saying inverse secant. If you need to write it as inverse secant, just to remind yourself, you definitely can, but these are the same thing. So if I'm using the arc secant rule, my rule is that the derivative, it would be 1 over x times the square root of x squared minus 1. But again, that's only when this is just an x. Here in my example, I actually have a 3x here. So when I'm going to use my formula, I'm going to have to replace both of these x's with that x to the, or the e to the 3x. So let's see. Our derivative, y prime, is going to be 1 over, again, our formula says x here, but it's not just going to be x, it's going to be whatever's in here. So 3x, or e to the 3x. And then underneath the root, it says I have an x squared here, but again, I'm not putting an x, I'm going to put an e to the 3x squared, and then I'm going to subtract 1. But again, I just have to be careful because if I'm following my rules here and I know that this is not just an x here, here's where the chain rule has to come in. Because again, whatever I'm plugging in for the x, I have to chain rule and get the derivative of that stuff too. So the derivative of e to the 3x is e to the 3x. And then I need to chain rule my exponent, so times 3. So I'm going to clean this up a little bit. So I can bring this 3e to the 3x up in the numerator. My denominator is going to become, again, just leaving that e to the 3x on the outside by itself, but I definitely can simplify in here. This is a power to a power. Power to a power means I can multiply these together. So this is going to be e to the 6x minus 1. And then I'm noticing that both of these are outside of the root. So these are really like terms here that I can, if possible, get rid of because I have an e to the 3x in the top here. I have an e to the 3x in the bottom here. So my final simplified derivative is actually just going to be 3 over the square root of e to the 6x and then minus 1. And that is my final derivative. All right, so it's your turn to get some practice problems in. Let me know if you have questions.